8.1, as we launch into Chapter 8, is going to get into working with some fractions and some radicals, but in order to get started, we need to really talk about variation and different functions that help us represent variation. And what I want you thinking about is what are some consistencies or some patterns within each type that help us quickly recognize what type it is when we see a formula or some sort of equation, right? Because really, every equation or every formula has these components to it, whether things are varying directly or varying inversely. So let's take a look. Direct variation. When we see something y varies directly as x, this is the equation we're looking at. Y equals kx, right? And that means that as x goes up, or as x increases, y increases. Or as x decreases, y decreases. Their values are moving in the same direction. Here's an example. Given y varies directly as x, and y equals 6.5 when x equals 13, write and graph a direct variation function. So this can be modeled with this function here, okay? Y equals kx, and k is the magic number. K is the constant of variation. That never changes. We substitute in 6.5 for y and 13 for x, divide both sides by 13, and we find out that k is 0.5, which gives us the equation y equals 0.5x. Now that's the writing of the equation. The graphing of the equation looks like this. Notice it's a line with a slope of 1/2. Rise 1, run 2. Okay, not too bad. Notice there is a point at 0, 0. There's no y-intercept here. This line, or this direct variation, will always pass through 0, 0. Notice, as x is increasing, as x is increasing, y is increasing. As x gets negative, y gets negative as well. They travel in the same way. Okay? So direct variation is that multiplying, go from there. I think that should be a pretty familiar concept. Just be thinking almost like slope, to be honest. Okay. What's a little bit new is inverse variation, which means y varies inversely as x. As x gets really large, y gets very small, and as x gets very small, y gets very large. The function that we're looking at is y equals k divided by x, k over x. And so that constant of variation, k, is now in the numerator while x is in the denominator, okay? Excuse me, sorry. Okay, so here's an example. Given y varies inversely as x and y equals 4 when x equals 5, write and graph an inverse variation function. So we need to set up the function y equals k over x divided by x. Substitute in what we know for y and what we know for x. 4 equals k divided by 5. And right there, this should not say multiply by 10. That's my bad. This should say multiply by 5. Because we're going to multiply both sides by 5 here to get that k equals 20. That means our function, our inverse variation function, is y equals 20 divided by x. Okay? So we can graph that. And the easiest way to graph this is going to be by plotting points. So when x is 2, y is 10. When x gets larger, y gets smaller. So when x is 4, y is 5. And when x is 5, y is 4. That's really what was the driving original ordered pair for this problem. And then over here, when x is 10, y equals 2. Notice I really only picked points that were factors of 20. And then I, of course, went negative down below. Okay. We get this sort of hyperbola-looking thing. So as x continues to get smaller and smaller and smaller and approach 0, the limit, or the y value, is going to get closer and closer and closer to infinity. We're going to have points way up here, right? When x is 1, y is going to be way up here at 20, which seemed like a little ridiculous to graph, so I didn't graph it. But you can see how this is inverse. As one goes up, the other goes down. The third one is joint variation. Y varies jointly as x and z. That means now I have two quantities that y is related to. And the function here is y equals kxz. Okay. Given y varies jointly as x and z, and y equals 24 when x equals 4 and z equals 4, write a joint variation function. This one doesn't graph as nicely because we have x, y, and z, so you start getting into 3D, and that's a little intense for us. But y equals kz, gotta find k. 24, plug that in for y, plug in x is 4 and z is 4. So 24 equals k times 16, and if we divide both sides by 16, we get k equals 1.5. So the function here is y equals 1.5xz. You might see this when we're talking about volume formulas, or talking about, what's another good example? Surface area, maybe? Right, where we're working with 3D objects and 3D variables, right? And so the volume of a cylinder varies jointly with the radius and the height, or stuff like that, right? We might have two variables that help us decide what the value is going to be. And that's where we see joint variation. Joint variation is pretty common in some of those real-world situations. Okay? The final one is called combined variation. And combined variation uses direct variation and inverse variation. They work together. Sometimes you'll see the direct variation happening in the numerator and the inverse variation happening in the denominator, right? We saw that a little bit when we looked back at inverse. We talked about x living in the denominator. Here's some examples of combined variation. PV equals nRT or PV equals nKT, the ideal gas law, right? Pressure and volume, E equals the number of moles times R, which is a constant, times temperature. And then over here, N represents the number of molecules, and K is a different constant, right? Not a huge deal, but this is an example of combined variation. If we divide both sides by V and have pressure alone, you'll see V will be down in the denominator. V varies inversely where temperature varies directly with pressure. Okay? So temperature varies directly. As the temperature goes up, the pressure goes up. Okay? Volume varies inversely. As the volume goes down, the pressure goes up, right? As you shrink the size of your container, the pressure of the gas inside that container has to go up, right? There's just not as much space for it to occupy. Another one is the gravitational force between two objects. This one might be a little bit easier to see it on because of the fact that we have one variable alone on the left side, which is the force between two objects. G is the constant, almost like that idea of K. And then we have the mass of the two objects. That varies directly with the force. As the objects get bigger, the force goes up, right? The gravitational force between two tiny little objects is not much, but the gravitational force between the sun and the earth, that's really something worth talking about. Okay, or the moon and the earth, right? Talking about tides. And then the radius between the two, that's what R stands for. As the radius goes up, the force goes down. As two things get further and further apart, they're not going to have as much of a gravitational pull or an attraction. Okay, right? It's inverse, or it's inversely related because it's in the denominator. Okay, so really, you've seen this idea of variation before if you've looked at these sorts of things in maybe physics, chemistry, and things like that. It's just a matter of we're giving them names and we're setting up some rules with them. So I think you're going to do just fine. Make sure you've got the three parts: y equals kxz, y equals k over x, and y equals kx, right? Because that's going to help you quickly recognize it, right? If you can recognize numerator versus denominator, things like that, that's really going to help you see, oh, this is inverse, this is direct, and so on. You can totally make this happen, people.